Discuss about timers. Basically, timers are the peripherals inside the 8051 microcontroller. Not only 8051, timers are peripherals inside many of the controllers. These are the basic peripherals, and this peripheral is mainly used in time-based applications. So let us see what are these timers and how we are going to use these timers in case of 8051 controllers. Now, basically, a timer peripheral contains some registers, and those are called as timer registers. And this timer works with, as it is a register, so definitely a register will be performing any operation when it is going to receive the clock signal. So here the same thing, timers will be receiving the clock signal from the crystal oscillator through some circuit. We'll see what is that circuit, and so it will be receiving the clock signal. Okay, and these are 16-bit registers. These timers are 16-bit registers, and there are totally 2 timers are present inside this 8051, and those timers are called as timer 0 and timer 1. And both of these timer 0 and timer 1 registers are 16-bit registers. Okay, now here these timers are mainly used for these functions, like we can generate the delay with the help of these timers, and we can count the events which are happening outside the controller with the help of these counters, and we can also generate the baud rates, and this functionality is used in case of serial communication. So these are the 3 important functions which can be done with the help of timers. Now here, if you are generating the delay, then that particular application or functionality is named as timer. Okay, don't get confused with the timer peripheral and timer functionality. Okay, so if you are generating the delay, then that functionality or application is called as timer, and if you are counting the events, then it is called as a counter, and baud rate generator when we are using it for the third functionality, that is generating baud rates for the serial port. Okay, so these are the 3 things that we can do with the help of these timers in 8051 microcontroller. Okay, and there are 2 timers, timer 0 and then timer 1, and both of these are 16-bit registers. Okay, see, if I'm using the timer register here, X indicates either 0 or 1. As I told you that there are totally 2 timer registers. So if one of the timer register, or if any of the timer register is used as timer, then it is going to get the clock signal from the crystal oscillator, that is 11.0592, and this frequency is given as an input to one circuit, that is divided by 12. Why? Because one machine cycle is nothing but 12 clock cycles. Therefore, this circuit is called as divide by 12 circuitry, to which we are going to give the input as 11.0592, and then the output of this particular circuit will be given as an input to this timers, clock input to these timers. Okay, and this frequency is 921.6 kilohertz. Therefore, these timers are going to receive the clock frequency of 921.6 kilohertz. Okay, now here it is going to count the internal clock pulses. Okay, if I'm using it as a timer, then it is going to count the internal clock pulses. Now, if I'm using the same timer peripheral as counter, then timer 0 will be receiving the clock signal from T0 pin, which we have already seen. Okay, and timer 1 will be receiving the clock signal from the timer 1 pin, that is T1 pin. Therefore, here these timer registers are now going to count the external clock pulses which are given through T0 and then T1 pins respectively. Okay, so if it is a timer, then it counts the internal clock pulses. If it is working as counter, then it counts the external clock pulses. Okay, now these are all the registers which are related to the timer peripheral, and if I want to use this peripheral, then I have to access all these registers. Okay, now here timer 0 register as well as timer 1 registers are divided into 2 parts. One is TL0 and TH0 for timer 0, and TL1 and TH1 for timer 1. Okay, lower byte, L indicates lower byte and H indicates higher byte. As this 8051 is an 8-bit microcontroller, so it cannot access or it cannot address a 16-bit register. That is why it is divided into 2 parts, that is lower byte and then higher byte. So as timer 0 is a 16-bit register, so it has two parts. One is TL0 and the other one is TH0. And as timer 1 is also 16-bit register, it has two parts. That is lower byte 1 timer TL1 and then TH1. Okay, so these are the registers which are basically used for holding the values. Okay, as soon as we start the timer, then these registers will be holding the value. It means the number of clock pulses that is received by the timer will be indicated by these registers. Okay, and then TCON is nothing but a timer control register. As this is a peripheral, so every peripheral will have a control register which is basically used for controlling the functionality of that peripheral. So with the help of this control register, will control the functionality of the timers. And then Tmode is a register which is basically used for selecting the mode and operation of the timer. Okay, so let us see these registers one by one. Initially we'll start with Tmode register. Okay, so Tmode is an 8-bit register, and here you can see these first 4 bits, that is from 7 to 4, that is MSB 4 bits or higher nibble of this Tmode register are for timer 1, and then the lower 4 bits are for timer 0. So if you program these 4 bits, if you program the higher nibble, then that gets affected to timer 1, and if you program the lower nibble, then that gets affected to timer 0. Okay, now let us see what is the functionality of each and every bit. Okay, so here this gate and all these 4 bits are similar to these 4 bits, but these are used for timer 1 and these are used for timer 0. Okay, let us see the functionality or importance of each and every bit. So gate bit, here if this gate bit is 0, then it means that we are using software control. It means we are controlling the timer with the help of software. That means software is nothing but instructions. So with the help of instructions, I'm controlling the timer. Okay, if this is an hardware, that is if it is programmed to 1, then it means I'm just controlling the timer with the help of some hardware. Okay, it means I have to use instructions. Along with the instructions, I have to generate an interrupt signal. Then only the timer gets started. Okay, so here software is nothing but with the help of instructions, and hardware is nothing but with the help of an instruction along with an hardware interrupt signal. Okay, and C by T bar. Here, as I told you that I can use this timer peripheral to act as timer or else to act as counter. Okay, so I have to I have to tell the controller before using this peripheral that whether I'm using it as timer or else I'm using it as counter. If I'm using this peripheral as timer, then this particular bit should be programmed to logic 0. If I'm using this particular peripheral as counter, then this particular bit should be programmed to logic 1. Okay, then we have mode bits, that is M1 and M0. These are called as mode bits, and here we have, as you have 2 bits here, therefore you'll get 4 combinations, that is 0 0 0 1 1 0 and 1 1. So 0 0 is called as 13-bit timer mode, 0 1 is called as 16-bit timer mode, and 1 0 is called as 8-bit auto reload mode, and 1 1 is called as split timer mode. Okay, so we'll see all these modes in the later slides. Now we have one more register, that is TCON register, timer control register. It is again of 8 bits. Okay, and here lower nibble of this TCON registers is related to the interrupts. Okay, and this higher nibble of TCON register is related to this timers. Okay, so we'll discuss about this lower nibble when we come across the interrupts. So we'll concentrate now on this higher nibble. So here TF1, which is nothing but timer 1 overflow flag. Okay, and TR1 timer 1 run control bit, TF0 timer 0 overflag bit, and then TR0 timer 0 run control bit. So with the help of this overflow flags, it is going to represent the overflow status of the timers. What do you mean by overflow? If I have a 4-bit counter, assume that I have a 4-bit counter. Now it starts counting from 0 0 0 0, and it reaches, as soon as it reaches its maximum value, that is 1 1 1 1. Then after receiving one more clock pulse, now this counter will be again initialized to 0, or will again starts its count from 0. So whenever this particular condition happens, that is from 4 ones to 4 zeros, then that condition is called as overflow. Okay, so whenever overflow occurs with respect to timer 1 or timer 0, then these two bits will become 1. If it is timer 1, then this TF1 will become 1. If it is timer 0, then TF0 will become 1. Okay, now after initializing the timer, then we have to start the timer. Okay, so that is done with the help of these TR bits. Okay, TR0 is used for start or stop of a timer 0, and TR1 is used for starting or stopping of a timer 1. Okay, for example, if I have a digital watch, so after initializing the digital watch, I need to press the start button, which is provided for the digital watch. Then only the clock runs, then only the timer runs. So here the same thing is done with the help of these bits. Okay, so after initializing the timer, you have to program these bits for starting the timer as well as for stopping the timer. Okay, if it is programmed to, if any of these bits are programmed to 1, then the respective timer gets started. If any of these bits are programmed to 0, then the respective timer gets stopped. Okay, and TF0 and TF1 are used for indicating the overflow status. Okay, now this is how the hardware which is present inside the controller for the timers. Okay, now let us see how this hardware works. Okay, so we have a C by T bar bit. Okay, and here you can see that oscillator frequency 11.0592 is given to one circuit, that is divided by 12, and the output is given to timer. Okay, and we are also getting, that is timer also getting the clock signal from the other source, that is T1 or T0 input pin. Okay, if this C by T bar bit is 0, then it would be working as timer. Therefore, this switch will be connected to this point. Therefore, this timer registers are going to get the clock signal from the oscillator frequency from this source. Okay, now if this C by T bar is 1, then it would be working as counter. Therefore, this particular switch will be connected to this point, and then it is going to receive the clock signal from the T1 or T0 input pin. That depends on the timer which we are using. Okay, so if it is getting the clock signal, then only the timer starts running. Okay, if not, it would be stopped. Okay, now this is up to this part. Now let us see what is this. So here gate bit, which is going to indicate whether you are controlling the timer with the help of software or with the help of hardware. If this gate bit is 0, it means we are controlling the timer with the help of software. So assuming that this bit is 0, okay, now here the output of the NOT gate is 1. So as one of the input to the OR gate is 1, it will not depend on the other input. Now this other input is hardware input. Therefore, it will not be depending on the hardware input. Therefore, the output would become 1. Okay. Now as one of the input to the AND gate is 1, now it would be waiting for the other input. What is the other input? That other input is coming from TR1 or TR0 bit in TCON. Okay. This is used for starting or stopping the timer. If you want to start the timer, then the respective bit, that is TR1 or TR0, should be programmed to 1. Therefore, 1 and 1 to the input of AND gate. So the output would be 1. Therefore, this switch gets closed. Now as soon as this switch is closed, then the timer register is going to get the clock signal either from this source or else from this source. Okay. Now assuming that this TR bit is 0. Okay, assuming that if TR bit is 0 and here this gate bit is 0, therefore the output of the NOT gate is 1, and as one of the input to the OR gate is 1, therefore the output of OR gate is 1. As this TR bit is 0, therefore the output of this AND gate is 0. So this switch will be open. It will not be connected to this particular point. As this switch is not connected to this point, therefore the timer is not going to get any clock signal. So it will not be counting the clock pulses. Okay. So in order to run the timer, definitely you have to give the clock signal. Okay. Now let us see the hardware control. So if this gate bit is 1, it means we are using in hardware control. Therefore, the output of this NOT gate is 0 now. So as one of the input to the OR gate is 0, then it would be waiting for the other input. Now what is the other input? So that depends on this INT1 bar or INT0 bar. So if you are generating any hardware interrupt, then the output of this particular OR gate will become 1. Okay. Now if this TR bit is 1, therefore the output is of this AND gate is 1 and this switch gets closed. If this TR bit is 0, then the output of this AND gate is 0, therefore the switch will be open. Okay, so this is how the hardware which is present inside the 8051 for timers will be working for timers to act as counter or else to act as time. Okay, now let us see how these registers are present inside the modes, that is mode 0, mode 1, mode 2 and mode 3. So here mode 0 is called as 13-bit mode. Why? Because we are using only 13 bits of the timer register. It might be timer 0 or timer 1 register. Okay, as you can see here, the lower byte of timer register will be using only 5 bits and the higher byte of timer register will be using 8 bits. So a complete of 8 plus 5 is nothing but 13 bits. So here we are using a complete of 13 bits. So that is why it is called as 13-bit timer mode. Okay, now as soon as when this particular timer registers gets an overflow condition, then this TF bit will become 1, which generates an interrupt. Okay, now here the minimum value that these timer registers are going to hold is 0000, which is represented in hexadecimal format, and the maximum value would be 1FFH. Okay, now let us see mode 1. Here we have again TL and TH, where X represents either 0 or else 1. That depends on the timer which we are using. As we are using a complete of 8 bits or 16 bits, then that is why it is called as 16-bit timer. Here the initial value is 40H and the maximum value is 4FH. Okay, as you can see here, TL using 8 bits and TH is also using 8 bits. Whenever this particular registers comes across the overflow, that is whenever there is a transition from this maximum value to the minimum value, then this TF will become 1, which will generate an interrupt. And the maximum amount of delay that we can generate with the help of this mode 1 would be 70 milliseconds. We'll see how to calculate that delay in the later slides. And we have one more mode, that is mode 2, and it is called as auto reload, and it is an 8-bit mode. Why? Because here we are using only the 8 bits of TL register. Okay, so we have to initialize this TL register with some value, and TH register should be initialized with an auto reload value. So assuming that this TL is started with 0, therefore for every clock pulse that this timer register is receiving, it gets incremented by 1 and reaches to its maximum value. So after reaching its maximum value FF, now if one more clock pulse is received by this TLX register, then it would be initialized to the value which is loaded in this TH register. So that is why it is called as auto reload mode, and for every rollback condition or for every overflow condition, this TF will become 1, which generates an interrupt. So that is why it is called as 8-bit auto reload. Why? Because after FF, this TL register gets loaded with the value which is present inside this TH register. Now let us see the third mode, that is mode 3. Now this is called as split timer. Why? Because the timer 0 is divided into 2 timers. Basically we have timer 0, original timer 0 and original timer 1 registers, but now in this case timer 0 will be acting as 2 timers, that is TL0 will be acting as timer 0 and TH0 will be acting as timer 1, and we have one more original timer 1 which is of 16-bit register. Okay, so in this mode we can use a total of 3 timers, that is TL0 as a separate timer, TH0 as a separate timer and timer 1 as a separate timer. Okay, so I'm calling here TL0 as timer 0. Why? Because all the control bits which are related to TL0 or timer 0 are used by this TL0, and all the control bits which are used by this timer 1 are now used for this TH0. So that is why it is treated as timer 1 and it is treated as timer 0, and we have one original timer 1 register and it doesn't have any control bits. Okay, now as you can see here, if this TL0 exceeds its 8-bit maximum value, that is from FF to 00, then this TF0 will become 1, indicating that an overflow is occurred with respect to timer 0, and here timer 0 is nothing but TL0. And in the same way, TH0, if it comes across the overflow condition, then this TF1 will become 1, indicating an interrupt or generates an interrupt. Okay, so again here TF1 has become 1 just because of TH0. Why? Because it is now treated as timer 1 and there are no control bits that are used for this timer 1. Okay, there is no TR bit for timer 1 and there is no TF bit for this particular original timer 1. and this mode is basically used whenever we want three timers. That is, for example, I want one timer for generating the delay, one timer for counting the events, and one timer for generating the baud rate. Then I'm going to use this kind of mode. And mode 2 is basically used in that is serial communication for generating the baud rates. Now let us see how to calculate the time delay. So here, for example, if I want to generate a time delay of 10 microseconds or 1 millisecond, then what I have to do? What are the values that should be initialized into the timer registers? Okay, so that is done by following this particular process. Okay, let us see here. The initial step that we have to do is we have to divide the required time delay by 1.085 microseconds. So here we got 1.085 microseconds from this, that is 11.0592 is divided by 12, therefore 921 kilohertz. So I have to calculate the time period for this, that is inverse of this frequency is 1.085 microseconds. Therefore, for every 1.085 microseconds, this timer register gets incremented by 1 when it is receiving the clock from the 11.0592 clock source. Okay, so here we have to divide the required time delay by this 1.085 microseconds. Then you'll be getting a value. Now here I'm representing it with n, and it is in decimal. Okay, now I have to subtract this decimal value from the maximum value of timer plus 1. What is the maximum value of a timer? Now here the maximum value of timer will be depending on the mode of operation. If I'm using in mode 0, then the maximum value of timer would become 1 triple F plus 1. That we have to calculate in decimal. Okay, and if it is mode 1, then the maximum value would become 4Fs plus 1, which is nothing but in decimal 65536. Okay, so we have to subtract this decimal value from this maximum value of timer, which should be represented again in decimal. Then we'll get the resultant value in decimal. Now we have to convert this decimal value into hexadecimal. Why? Because controller understands hexadecimal value. Therefore, convert this decimal result into hexadecimal. Then you'll get 4-digit hexadecimal value. Now this 4-digit hexadecimal value should be loaded into TH as well as into TL. Okay, it might be TH0, TL0 or TH1 or TL1. Why? Because that depends only on the timer which the user is using. Okay, so this is how we are going to generate the time delay by using the timers. Thank you. In the next session, we'll discuss about serial communication.